we're looking at a certain level of function. So we can visualize that finding a level like the lambda here, and finally, both these problems, as we calculate the equivalence geometrically, equivalent to slopes. So here I have a picture of the famous idea of the teacher every Okay, so we have 5 pieces we will talk about there. The last one. We talk about optimization, we talk about equation solving, we talk about calculating slopes, and then we're doing for the which is actually generalization, differentiation, and doing piecewise linearization. Okay, so here we come to optimization. Many people think of climbing the hill of finding maximum, and in optimization, we actually prefer to talk about minimization, which is of course mathematically equivalent. So instead of finding a maximum, you can equivalently find a minimum minus the original objective function. So mathematically, there's no actual difference whatsoever. This is the famous line on Titicaca in the north of Chile. So the historical background is Cauchy, as far as we know. Before that. Published the first optimization method in 1864, and he suggested what's called steepest descent, which seems very natural, and which is still well known as steepest descent. So what we're doing is we're taking the function f here in 3 variables x, y, and z, and we try to adjust those variables x, y, and z such that we get closer and covering the sufficient number of iterations arbitrarily close to a minimizer. And we do that by changing x in the direction of the derivative of f with respect to x, multiplied by a small number alpha. If the alpha is too large, you might overshoot and not back to a minimum. But for sufficiently small alpha, we can show that this iteration, so minus equal means subtract the right side from the left side, and that's the new integral x, y, and z. For sufficiently small alpha, that's not good. And Cauchy already suggested the extension of this to solving systems of the equation. So if we have 3 equations, u equals 0, e equals 0, w equals 0, each one of these equations being functions in x, y, and z. Then, of course, we find the roots by minimizing sum of squares of u, v, and w. Now, that's actually turns out to be a very bad method which nobody uses anymore. It's also kind of interesting that at the time, Cauchy said, I limit myself to communicate the principles of the method, and later on, I will write another paper which will the details, but we never got around to doing that. Next slide. So here is a well-known test function, the Rosenbaum test function, which has the value where x2 is equal to x1 squared. That's the value you see there. And as soon as you get away from this value, the function grows rather rapidly because that value is squared, and also because we have this prefactor of 1. And then there's an extra term which pushes the x1 plus 1. So the minimum is attained at this point here, and that's the only minimum where the function is 0, obviously it can be non-negative. So now we can see the next slide, how steep descent. Well, firstly we see what the contours look like, and as I said, it has the minimum is at 1, here at the bottom of this curve, and most optimization methods in particular, steepest descent had quite a trouble in dealing with the next slide and dealing with this curve gully. So if we start steepest descent at this point, where it says start, then it takes one step really swiftly down to the bottom of the valley, and then it has a long run along the curve bottom of the valley until it finally reaches the solution. So that may take some 70 iterations or so. Now, of course, the game in numerical mathematics is to minimize the computational effort. That means minimizing the number of iterations, minimizing the function, and in this case, also the derivative, the gradient evaluations. And 70 steps is much too high. So what can we do? Well, we can actually convert this problem into the second problem by this solving equations. So the next slide says we're going to go to the gradient solver. As I said, we can think of that as finding the level of the next slide. So for the minimization of the function f in the two variables x and y, like you probably know from school, you find the minimum and you set when you set the derivative to 0 by setting the derivative to 0. And here we have two derivatives, the derivative of f with respect to x and the derivative of f with respect to y. We call these things partial derivatives. And in case of the Rosenbaum function here, these partial derivatives are easy to calculate. We differentiate this with respect to x, we have of course x minus 1. This is a little bit more complicated. It's similar derivative here with respect to y. And in order to calculate the minimum, what we now can do is to call this component g and this component h and solve the system of equations 0 equal g and 0 equal h. How does one solve equations, systems of equations? The most popular and so says really the best method is now called Newton's method, and that's based on a multivariate Taylor expansion. So what you do, we are going x and y, and you can bring that x and y, so that g and h evaluated at this new point are 0 and really exactly 0. But that's not so easy to do, so what we do is we expand the function by Taylor. So we have g and h here, and we have the derivative of g with respect to x times delta x, the derivative of g with respect to y times delta y, and so forth. Setting this to 0 means solving the linear system in two equations, and that's easy to do, provided this matrix, the so-called Jacobian pressure matrix of g and h with respect to x and y, is non-singular. Yeah. Stationarity condition means the gradient is 0. At this point, the function is flat, which happens at the maximum, it happens at the minimum, and it also happens at the saddle point. So the function is stationary up to first order. So if we go to the next slide, yeah. So we have to be able to differentiate, and we have to be able to solve this linear system. That's not really a problem. The question everybody assumes that was done by Newton, differentiation and Leibniz, and then the French who came up with the concept of the derivative, which was eventually resolved by the Royal Society of England in favor of Newton, and it's ruled that he actually wrote the expertise to justify that decision. So for a while there was a division, there still is in some way between the Leibniz and the Newton notation between England and the States. This is the problem. But in fact, you can trace back this idea much earlier and actually did optimization. So some scientists in Iran, he examined the solvability of a cubic equation like this, and x equals x squared a minus x, and asked for which values of this constant c here is this function has a solution. In those days, we were only interested in positive solutions and real solutions, of course. And in order to find this limiting c, we maximize this function. And we maximize that by using the derivative. course, he didn't monitor the derivative, but he has exactly the right expression. So really, we should be talking about the Newton Malthusianism. And similarly, it was found that in the medial section of Kerala in the late 1300s or 1300s, or the power series were used by scientists for celestial mechanics. So they have power series invented, trigonometric functions, and they're invisible. Okay, so I'm going to try to do some numerical calculation. Hopefully it works. So we had the Rosenbrock function, we had the stationarity system. I'll show you in a minute that Newton's method converges very rapidly in just 3-4 steps on the stationarity system. And then we're going to look at another objective function, which is also a very simple polynomial, and it has coefficient epsilon and the result of certain R here. And we vary that. It turns out for n equal to 1, this is just a regular system. Yeah. Well, the stationarity condition is the first order condition. Of course, often one is interested almost to distinguish between maximum limit and saddle point. And then we have to look at second derivatives to try to converge. But I cannot be able to say anything about that. Well, saddle points are points where the second derivative matrix has positive and negative eigenvalues. So it only has positive eigenvalues, we have minimum, or negative eigenvalues, we have maxima, and when it has 0 eigenvalues, which actually can happen here. This is the interesting case, and that's where it needs some contribution. When we have n equal to 2 or 3, the stationarity condition becomes singular in the sense that this Jacobian at the stationary point, which here is the origin, is singular. And then it wasn't really known, it's not clear what happens to Newton's method. And I can see some pretty interesting thing happens, and that's what I'm trying to demonstrate. So if you look at the determinant of this matrix, it's n, so that's the order here, n times n plus 1, times epsilon times 0 to the n minus 1. Well, in mathematics, 0 to the n minus 1 is 0, but n is not equal to 1. When n is equal to 1, it's 0. So it's equal to, so when n is equal to 1, 0 to 0 is 1, and we get 2 epsilon here, and otherwise we get 0. So let's see whether I can get this here to work. And in the singular case, that's where I have made a contribution. So here is a Python program. So firstly, let's look at the Rosenbrock function. This is just a way of coding up the Rosenbrock function in Python. It's fairly intuitive. So we compute the function RBF. The partial derivative with respect to x, the partial derivative with respect to h, and we calculate the 2x2 matrix of the derivatives of g and h, which happens to be symmetric, so B will be equal to C. And this piece of information, we get Newton's method now. Here, what does the Newton method do for a certain number of steps? I said max equal to 15. It stores a very current position for plotting later on. It computes the determinant, and with the help of the determinant is able to easily solve the 2x2 system of linear equations. So we get the change in x and the change in y, and we subtract that from x and subtract that from y, and then we put the whole thing out and we really plot. So by run that, So next in 15 is really not necessary, as you see here. In the beginning, the function value at the starting point is up here, somewhere close below 2x and close below y. Close below 4 and y. So the function value at the initial point is actually quite big, 9.22. So it's a very substantial gradient with respect to x. And here we have the exponential. Now what I've plotted in the last row is the ratio between the ux minus 1, well actually the ux and the OX is not very smart. Here I've written down the determinant. You see the determinant is always non-zero, so you can solve the linear system without any problem. And the function value goes from 9.2 to 0.8. Then it jumps to 57, but then it goes down to f more or less equal to 0. One or two iteration reaches x equal to 0, x equal to 1, and y equal to 1. So here on the plot, you see we start up here, we take a little step down the hill, then we take a big step left and straight, and then after a couple of iterations, we have the solution, which is 1, maybe down with all the available accuracy. So now let's change this angle to 1. And when I have n equal to 1, this is one of those problems that I said was actually, oh, that's the regular thing for this problem that is singular. Well, let's go directly to it. So here's a function that I call singular, because for n equal to 2, 3, or 4, the totally and the solution, which is the order, is in fact singular. So the usual theory of the convergence of Newton's method does not apply. So I have to change this to zero. And then we see what happens. Oh, now I have to give it the epsilon, and for n equal to 2, I was going to give it a 4. And here you see we do get convergence. This is a stationary point that's actually not a minimum, so at the origin, the gradient is 0, but in this direction we can go downhill, in this direction we go uphill. We start the integration up here with the first guess of the solution. It jumps there, and then it approaches the solution along the direction x. The x direction is actually the one, the null vector of this machine. So what can show very precisely is about the way this approach happens. The key thing is the ratio between two successive values of x converges exactly to half. So the immediate iteration reduces the distance to the solution by 50% of each iteration. Now you can easily convince yourself in the one-dimensional case that happens, but that happens also in systems with large model, provided the large space is one-dimensional. So now let's go to the situation, the interesting thing, the situation where we have this equal to 3. When m is equal to 3, and we let it run. I have to give you the epsilon. The epsilon I'm going to give you. The first one is also forward. And here the situation is pretty similar to the one we had before. Now we do actually have a minimum. This is again the null space, the right null direction, which is a bit bigger. We start out here, we come along the null vector, and this time the reduction is not halving, but it's a reduction by a number that's somewhat bigger than 2/3, and that number depends exactly on this coefficient epsilon. And so this is still very nice and regular, but when I change the epsilon so when I give the epsilon to the right point of V, it was a good sense to start with that. So here we start again from the same point, and we get an interesting alternating pattern. It jumps from here to there, then it goes down to the bottom of the valley, then it takes up the tangential along the valley, and alternating it converges to the minimizer at the station which is here, and the rate is still reasonably satisfactory, but of course I would like to be faster. Now, if I run it again and change the absolute value to 0.905, then something really weird happens. So, we should have looked at the numbers. We look at the numbers, we see at first it seems to make some progress, but then all of a sudden the x starts to grow from 1.7 to -2.85, and in the end it's 5.2. The function value is 111,000 and so forth. So you can show that you can start actually close to the stationary point of this degenerate minimizer. The iterates for this particular value of epsilon, there is a small neighborhood about it. They may look like converted for a while, but then they actually run off to infinity. Unfortunately, I have a number of iterates. But that's an observation that we made and that was published, I think it was completely new, which means that on a very simple smooth problem, namely a system of two polynomial equations with two variables, Newton's method can really run completely astray. So here are the results for Newton. Firstly, in the non-singular case, that's when n is equal to 1. When epsilon is not equal to 0, we will show that the ratio between the new error and the old error squared is bounded above by 1 less than infinity, which everybody knows to be the quadratic version, and that theory is usually credited to Cantor. If m is equal to 2, which means this extra term becomes cubic rather than quadratic, then we saw, and I can show under much more general assumptions, that the ratio between successive errors converges exactly to the half. I mean, that's so automatic. If we look at m equal 3 and take epsilon is sufficiently positive or sufficiently negative, then the ratio converges to something which is about 2/3. Mostly a little bit bigger, but it can also be smaller. And if you move the epsilon into this period region here, algebra is used, so we can have chaos in the sense that the cycles are through the length, and there also is iterations that run off to infinity. Okay, so this was the equation solving part, where in the singular case, we could make some contributions some 20, 30 years ago. It was essentially the middle part, is essentially the content of my PhD thesis. Next slide. Oh yeah, here's a graphical representation. This is actually the singular phase for E is equal to 1. Green means we converge to the root. The root is here. And the non-spacing is a little bit negative. And oh, let's go back. Sorry. What I should have stressed is this, the first result, incomparables, applies on all starting points that are sufficiently close to the distribution. All this singular stuff only applies to almost all starting points. This almost can be specified very accurately. Geometrically, what we see now in the next slide shows that we have convergence from almost all points, except we have this channel that's cut out here. And we actually, beyond just promoting how movements method goes wrong in the singular case, we did some modification in order to recover the speed of convergence. And on the right side, you see that everything is on the neighborhood of the root now is green. So from there we get convergence, and the fact that the color is lighter green means that we actually converge to true iteration. Okay, now we go to the next slide. This is about the sign review article that I wrote on solving linear equation with simple singular reasonable nearly simple solutions. So that came out in 1984, finished like this in 1980. And you see there was quite some interest in the beginning. Then it happened a little bit, but in the last few years, there's been a lot of interest in getting singular systems. There's some Chinese crowd who did that. Now, this publication was cited 131 times, and the other publications were on this area, which I wrote not by myself, but with my supervisors and other collaborators. There were about 400 citations. Now, since we have citations, let's go to the next slide. And this is the book. I'll tell you, the book is called Evaluating the Movement Principles and Techniques about Movement Differentiation. So this is about how you get the slopes. They came out in 2000 and then stayed both until 2014. I can explain what the drop-off is here. But the overall number of citations right now is 2,263. And Simon, the American Society of Industrial Mathematics, published 2 versions of the book. So the second edition came out in 2008. And the sales figures for each of the editions was about 1,000, which for a rather specialized book is quite good. And this is the only book in town on the matter, but we managed to really convince everybody to use all terminology and notation in practically all applications on people. So next slide. Okay, here's a cover. There's actually the meteorological application which I don't have the time to explain. So this stuff is being applied to very large graphical models. The next slide, on the right side, we are currently in a contract design to write a book of numerical methods for non-student programs. And that's going to be the last part of the talk. Next slide. So what is this about? This is about slope calculations. And slopes are derivatives. Next slide. So again, you're trying to calculate the slope somewhere here. How can we do that? There are certain methods. The first one, next slide, is doing the derivatives symbolically, like you do it in school or also in calculus 1, calculus 2. You sit down, you assume you have a formula, you work out the derivative, and you can do essentially the same thing using matrix and and so forth. The nice thing is the derivatives are in principle exact. Drawback is the computational cost. As soon as the thing gets a little bit more complicated, you try to make it more absolutely a huge expression. And what you look at doesn't really give you much information. Next slide. Now, another very popular method is finite differences. You just evaluate the 2 different points that are reasonably close and divide the difference in the function by the increment and the argument. That's very simple to do numerically. Drawback is it's inexact, you always make a mistake, and as you'll see, the computational cost is also unnecessary. So what else could there be? Well, this thing that we call fundamental parameter differentiation. Next slide. So I look at a little example here. We call it the lighthouse example. Suppose there's a lighthouse here, and if this ray of light, and the ray of light is rotating like this, and we look at the angular velocity omega, and we look at the point where this ray hits the keyhole. And we do orbits y1 and y2 of the keyhole that are our dependent variables. So we want to calculate y1 and we want to calculate y2. Given three parameters about the geometric layouts, u, the slope of this keyhole, the angular velocity, and the time t. So we have four input parameters and two output parameters. Values and variables, we want to calculate the derivatives. In particular, if we calculate the derivative with respect to time t, we get the velocity with which this point moves along the keyhole. So next slide. Now, if you give this formula to a computer, it actually does, it breaks it down into elementary operations. First, we assign these four input values to, we call them x1 through x4, we assign them to local variables, and then we compute a lot of intermediate quantities. The first thing would be omega times t, and this notation d minus 1 times t1. We say that's an elementary function in the two variables b minus 1 and b0. Then we compute the tangent, which is an intrinsic function with the sine, exponential, square roots, all these must be provided for. Take a difference, we take the multiplication, at the end of the day, we say the intermediate quantities b6 and b7. Those are the two quantities that I'm really interested in. So anything that happens on the computer, in principle, can be interpreted in terms of the denomination of a function as a sequence of such elementary operations. Now, if we want to differentiate, next slide. Suppose we want to differentiate with respect to time t. We say the derivative of the first variable b0 with respect to t, we call it b0 dot, and that is 1. The other, the three geometric constants, I keep constant. And then I go again through my evaluation trace and add to the original calculation the corresponding derivative calculations, which are roughly twice as expensive as what I did here. But of course, there's a complete regular pattern, so you can do this extension by a piece of software, like in a way symbolic package does, but here there's no blow up of code or anything. At the end, we get the derivative of the outputs of y1 and y2. Okay, next slide. So geometrically, I can interpret it as propagating tangents and mapping f from a vector x into a vector y. And now I'm interested in what happens when I move the vector x along a certain smooth curve x of t, which has a tangent x dot. Then there will be a y, and also be a smooth curve, and the tangent will be y dot. And the y dot is algebraically the derivative matrix, the Jacobian of f, times this input tangent x dot. And we can calculate that using this extended procedure at a cost that's more or less the same twice t times as evaluating x by itself. And there is a reverse procedure that the next one. We can also compute the Jacobian multiplied from the left by a vector, which we usually call by bar. There's a certain geometric interpretation, which I can explain in a hurry. So y bar times f prime of x is x bar. Now we want a calculation which gives x, and y bar calculates that x bar. And for that, next slide, we can calculate